Firstly, thanks so much for the invitation. Maybe I'll just take a minute for the background. I grew up in Kerala. I went to Chennai for college. I've been to Bangalore several times, but not to the institute. So next time I'm in India, I'll definitely stop by. It seems like an amazing place. The other thing is that, yeah, it is the preceding speaker and the next speaker are two people I've studied probability with. With Jonathan Mattingly, I studied at Duke when I was a graduate student, and I've continued to work over the years. And Gareth did my postdoc with, so it's a really nice coincidence. I have been working on many aspects of Markov chain Monte Carlo. And especially in the last few years, I've been interested in the mixing times of discrete systems. But today I thought I would just, because this theme was an applied probability, I thought I will just talk about a set of problems that was motivated by working with engineers. They had a problem to solve, and we really had to invent methods. And you can really see, hopefully you'll see how applied probability helps us truly solve problems in this, in which it was not easy to implement some of these algorithms before. All right, and this is collaboration with these set of colleagues. Most of them are in MIT. And so I'm going to talk about computationally intensive problems where the difficulty is in evaluating a function, and I'll give you a motivation for this particular problem. But this problem, although I'm only going to talk about it in the context of a specific example, it has wide applicability. In particular, it is very relevant to problems with large data sets where computation is difficult as well. So the theme is that these are MCMC methods, Markov chain Monte Carlo methods, are extremely useful but time consuming, and also equally interesting and challenging is their design, right? To have algorithms that run on time. And one aspect that I do want to focus on in this is that I'm going to talk about something called an approximate MCMC. I don't have time to go into all of the details, but there's, in general, that we know how to analyze Markov chains, but if we do not know how to, or we do know, but not quite as much, where understand the properties of approximate Markov chains, where the Markovian kernel is approximated at various times. I know this has been an active area in the last several years, including the next speaker who's done a lot of work on this, but still so much more work should be done because it's immediately connected to applications. Again, hopefully I'll give you a glimpse of what I mean by this in my example. Okay, so here is the outline. I'll start with a motivating example from a computer experiments, and then I'll review what was known before our work, and then I'll explain our work in this. Again, please feel free to stop me midway for questions. So here is a motivating problem where Yusuf at MIT was studying. So what people were interested in is this example. This is an example of ice sheet dynamics in Western Antarctica, right? So we know that ice sheet is melting. And in particular, this is a photograph. You can really see that, and this particular place is something called Pine Island Glacier. Yeah, it's around here in this left part of the map. Let me just see if I can draw pictures. Okay, so it's on the western part of Antarctica, and here is and what people wanted to know is are the following questions, right? This is the interface of the glacier and water, and they wanted to know how readily is heat absorbed by ice, and how much mixing occurs in the ice-ocean interface. Can we infer these parameters to calibrate our models? These are the questions they were interested in. Okay. Now, how did they get these? How do they solve these problems? Well, these were they were using there's a simplified form of the Navier-Stokes equation. And it's quite complicated to solve. In fact, people write their PhD thesis and solving this one instance of this equation using very sophisticated finite element methods. And as far as I'm concerned, I treat this as black box, right? Where as a statistician, what I consider this is that given the initial parameters and the data, the equation can solve, right? But other than that, I don't know anything about the equation. I don't know how it is solved. For me, I consider almost as a black box. Okay, so now let me explain the problem. So what, by the way, and this is a huge area generally known as data assimilation, where how do you combine with scientists can try to combine physical models with data and to have statistical models that basically do not ignore the underlying physical model and still do inference and get parameter estimates. Okay, so here is the problem for us, right? So what we want to know is the posterior distribution of the parameters from the data and the underlying physical model, which is the partial differential equation I told you, right? So even if you've zoned out so far about the specific nature of the partial differential equation, you can ignore all of that. For now, that was just a motivating problem. But so the point is that you have a set of parameters that you want to understand, the posterior distribution of that. You have data observed from it. This and the underlying likelihood is coming from this PD. So, and you can really think of the, you can take a simple Gaussian errors for the likelihood function, but the specific nature of the measurement error is not the problem here. The problem is that we do not, each evaluation of this function. So what do I mean? So for a specific parameter values, solving this PDE once, using this computational systems they've developed takes hours, right? So this is the problem. So let me just pause here and ask for questions. It's because the setup of the problem is important to appreciate what is coming. So let me just pause here for a minute and ask for questions. Is this okay that the motivation is clear? I cannot see chat, but okay.
It seems, yeah.
Okay, great.
Nobody has any questions at the moment.
Okay,
I will follow the chat to help you. Yeah.
Yeah, terrific. Thanks. Thanks, Kavita. So, I don't even want to go too much into the dimension issue first. Let's take D is equal to 1, right? So this is let's assume this is a one-dimensional problem. There's only one parameter whose distribution you want to know. So if you could evaluate the function properly, right, which without much difficulty, this is a really known and solved problem, and this started the Bayesian revolution in 1990s when when the computers were up to speed. This is extremely well known, and there are many algorithms that are useful for solving this problem. So, for example, this is a cartoon that I've just drawn here, where you have there are 3 different distributions going on here, and the green distribution is the posterior contours that you want to explore. That is the distribution you want to explore. And you can really think of an MCMC algorithm doing local proposals. For example, this is the simple random walk metropolis Hastings, where wherever you are, you just look locally around it. And then you do accept reject mechanism, right? And this works like a charm, and probably the top algorithm of it was known as the top algorithm in the top 10 algorithms of 20th century. Okay, so again, I'm just in case anyone have not seen this before, I just wrote it down what the acceptance probability is. So here is the setup. Is your current value of the Markov chain. You set up a transition kernel. Here I'm just, for simplicity, I'm just using random walk metropolis. And then once you have the proposal, you construct an accept reject ratio. Um, and then you decide to go to the next point with that certain probability, right? So this is the classic algorithm. Now notice that in our problem, to implement this algorithm, you need to evaluate this likelihood function, or equivalently that this complicated function that is coming from the PDF twice, right? So if you're running the algorithm for n times in order to get n samples of the parameters, you have to at least evaluate the what I call the forward model, which is the PDE equation, at least n times. So clearly, if each evaluation of the function takes hours, this algorithm is just prohibitively expensive to be run. Right, and by the way, the applications to large data set is almost like easy to see also, where in that case you have even in the simplest case of IID data, if n is large, where n is a number of data points, you still have to evaluate this product form, or actually take the sum of the logarithm. You take a sum of n terms, and still, if n is prohibitively large, then this function is expensive to investigate as well. So some of the ideas, at least I'm mentioning here, are also applicable in this problem as well. Okay, all right. So what was known, so just to repeat, so what the difficulty in this problem is that how do you make this algorithm practical where it is expensive to evaluate a single time this likelihood function? So what was known before our work in this field? There were many interesting ideas. I'll review a few. One of the important idea was surrogates. It was started from the 80s. The main idea is that they would evaluate the function on a set of contours before even they look at the data, right? They will evaluate the true function on a set of contours, and then they'll approximate the function on the rest of the space, right? The problem with this is that they typically chose the set of points they evaluated the function, the true evaluations of the function before they started the algorithm. Now you can really see what happens is that you don't know where this posterior distribution is concentrated before you actually look at the data. Therefore, even if you evaluate the functions on a set of grid points, the places where you evaluate the function may not be where the likelihood or the posterior distribution is concentrated. Therefore, you might not be able to approximate well, right? Where you will approximate the function in places that you do not care about, and you do not approximate the function well in places that you actually care about. But this is a very important idea. And the next came some more prior work on this, which is that, well, the problem with what this was is that, well, you don't know where the mass is concentrated before you look at it. So any approximation a priori does not solve the problem. All right. So what next came, but this is a relatively still recent, maybe like 80 years ago or so, where what people did was, well, you run the algorithm for a while, and then you figure out where the function is roughly concentrated in. Now you get your grid points, approximate then, and then continue with your algorithm, right? So just to be clear, what is done here is that they'll run the MCMC algorithm for a while to understand where the function is concentrated, and then they approximate there. But the problem with this is that we don't know when to stop the approximation, in the sense that in this method and the previous methods as well, in these two ideas that I've just told you, we have to decide when to stop the approximation and then when to continue running the algorithm. So the problem with that is that you do not get to balance to have a trade-off between the sampling error versus the approximation error, right? For example, if you really want to compute Monte Carlo average of the functions, you do not know if this error is coming there because you are approximating a true function, or is it because the algorithm hasn't mixed yet, right? So this is the key problem that we wanted to solve when we were studying this problem. Okay, so let me pause there in case people have questions so far on this, and Kavita, if there is questions, please feel free to read it out. Okay, so our solution for this problem is the following. We take a completely different approach where we seek for asymptotically exact MCMC, where what we want to do is to do posterior exploration and surrogate constructions simultaneously, right? So the key idea here is that we do not want to live with finite approximation error. We want to have a mechanism in which, as and when the number of steps of the algorithm increases, we get to approximate the function to a precision that we want, and yet have exact posterior distribution, right? So that there's no approximation error in the posterior distribution, right? So this is the goal, is to basically not have finite approximation, but have approximation to have a method that you can have infinite refinement of the target function, but yet not evaluating it every single time when we want to take a step of our algorithm, right? This is the goal. Now, there is a key connection with the delayed acceptance schemes, maybe, and this is perhaps the closest to our method, but this method also still requires one full model evaluation per accepted sample. The idea is that what these Christensen and Fox do is that they construct a proxy of the function first, and then have an algorithm. For example, they can have a simple random walk metropolis or any other algorithm where they construct it on a proxy first, and if that accepts, then they use the true function to evaluate. So basically, they want to know this algorithm whether will we accept a sample or not, and then only evaluate the true function if you're accepting it. It's an interesting idea, but however, it still requires an evaluation of the function, which is the problem that we are trying to avoid. Okay. So just to see, again, reviewing the notation from before, Q is a proposal kernel. We're simply using, let's say, a random walk metropolis. This is the function. This is the acceptance ratio from the metropolis Hastings that comes in. And notice that L is hard to compute. So what we're doing instead is the following. Here is our method in one slide, and then I'll go into the details of the method. So what we want to do is initialize a set of S0. We evaluated the true function. And at every step, we would, instead of our true f being a true function, we will have ft, which is an infinite sequential refinement of that function f. Evaluated, how do you construct this function? This is an approximation of the truth, which is, and how do we construct that approximation? Well, st is the set of points where the function has been run. So these are the set of points where the function is truly evaluated. And the f, once you evaluate it on st, the rest of the points, the function, we construct an approximation. And the point is that we are going to grow st slowly as the algorithm progresses. So the size of the st must be n for the previous algorithms, where n is the algorithmic step, whereas we are trying to grow st slowly and still make this algorithm ergodic and have the right invariant distribution, right? So that's the goal. Okay. All right. So I'll just skip this slide. So our algorithm actually uses three natural statistical ideas. So notice that the goal is to make this work, right? That's the emphasis. So it uses three natural statistical ideas. One is local approximations. I'll tell you in a minute what I mean by this. Second is this idea of cross-validation. I have not seen this used much in MCMC ways. Like cross-validation is a very important idea in mathematical statistics and uses in machine learning, all of that, but I've not seen these ideas used in MCMC world. So there's so much more to do here. And the third one, this idea of experimental design, it's a field of statistics that's been studied well, but not, again, surprisingly not used in the design of MCMC methods. So, and again, there's so much more work to be done in this area. Okay, so here is the idea. The first idea is local approximations. So one of the things that we wanted to do is that we are only interested in evaluating the function locally. Therefore, given the set of points that we've already evaluated the function, the true function on, we constructed a simple local approximation. There are many methods in statistics that we know not just in statistics, but also in optimization. We use this local regression idea where you can use a simple quadratic regression, which would roughly require O to D squared points so that the problem is not underdetermined, and then you can construct an approximation pretty easily using a simple regression procedure. So the advantage of this local regression is that this has big literature in derivative-free optimization. You notice that we're not computing derivatives at all for computing this approximation, just only the function evaluation at true points. But it turns out that if the true function is smooth, we not only can we approximate the function well, but we can also approximate the derivatives well. And that's super important for us because here in this talk, I'm only talking primarily about random walk metropolis, but you can also construct other proposals such as Langevins, etc., where the proposal has a gradient of the underlying target density. Therefore, if you also get to approximate the gradient well, then that's just 2 for 1, and that's extremely useful. And this is really easy to implement. There are software packages in R, Python, etc. This will just do this for us pretty easily. So what we do is, just to be clear, so what does in this approximation step, what we do is at every point that we want to evaluate the function, if we choose to approximate, what we do is we go around in a radius of R, so that we get about O to D squared points where the true function has been evaluated. And then once you found O to D squared points of the true function evaluation, you just construct an approximation. So what happened is that in the initial run of the algorithm, when you actually find, when you have to go find points, O to D squared points, you have to go really, really far because you haven't evaluated the function in that many points. But the algorithm goes on. You don't have to go very far to find the function that is truly evaluated on a set of points, right? Okay. So that's number one. Step two is this cross-validation. So let me explain what this idea is. So okay, so at every step, you have to decide: are you going to evaluate the function, the true evaluation of the function? Are you going to approximate? So what we do is that, of course, if you want to have an infinite approximation, you have to evaluate the function infinitely many times. There is no way around that, right? There's no magic there. So, but what we do is that we choose at every step, with a small probability beta t, we choose to evaluate the function truly, right? So we actually compute the PDE and bear the computational cost. The rest of the time, we approximate. And we also choose this beta t. Let's say beta t is equal to 1 over t, so that the summation of beta t is infinity. So we do know that by Borel-Quintelli that you will evaluate the function infinitely many times. It's actually also one of the places where I have actually used in Borel-Kentelly in an application, and that's crucial. That Borel-Kentelly is crucial for this to work, right? So you can really choose beta t to be any slowly growing sequence which sums to infinity, and by that, but because it sums to infinity, we'll know that we'll eventually evaluate the true function infinitely many times. Okay. The idea of cross-validation is the second part of this step, which is that you want to know notice that as the better the proposal and better the design of the algorithm, the better the ergodicity properties of the algorithm, right? So that's why the design is important. So the way we are doing cross-validation here is that we want to know how good this approximation of this function is, right? So in case we should decided to not evaluate the function, true valuation of the function, and in case we actually do approximation of the functions using the previous algorithm of the local regression, we still want to know how good our approximation is. So what we do is we remove one point. Let's say we're using d-squared points to compute the approximation. We remove one point at a time and construct the approximation using the rest of the points. And so we have two different acceptance probabilities. One is the acceptance probability computed using the approximation of all of the d-squared points. And the alpha I plus is the acceptance probability that is computed by the approximation using all but one points. And the idea of cross-validation says that these two numbers should be really very close to each other. The point is that if this is not really close, let's say alpha I plus is substantially different from alpha, that means that this point I is unduly influencing the approximation. And in particular, the approximation could be bad because it's mainly influenced by one point, right? So this idea of influence is really a classical concept in statistics, for example, in regression and other problems where if you're running a statistical procedure, you really want to know if is there a particular data point that is unduly influencing your procedure, or the variation is coming from all of the data points. So that's what I call cross-validation. And the third one is experimental design. Again, it has connection to optimization, right? Where in case we decided to evaluate the true function, we still have to decide where to evaluate it, right? So one natural candidate to evaluate the new true function is where the new point is proposed by the algorithm. That is one way. But other ways is to think about how do you sort of space out your points of approximation so that the approximation algorithms give you a really good answer, right? So this has connections to space filling design, where and the maximum designs, etc., where classical optimization and statistical theory tells us that if you really want to know where are the points you should evaluate a true function to approximate well, there are designs that naturally tell you where to do that. Again, I'm not going to go into that, but there are software packages that tell you how to do that pretty quickly. So those are the three methods. Let me just review these three methods again. So the idea is the first one, you use local approximations and use the derivative-free methods that approximate the function well. The second one is that using this Borel-Kentelly idea, you can you get to evaluate the function every once in a while, and the rest of the time you approximate. And the idea of cross-validation basically tells you that how good is the approximation? Is it really be influenced by a single point or a group of points, or is it actually uniformly influenced by all of the data points? And the third one is the idea of design, where you get to decide where do you evaluate the true function, right? What is the most optimal way to do that based on what you've seen so far? Okay. Now, and now comes truly, okay, well, the algorithm seems like it makes sense, it's natural, but now we need to go back to the mathematics and say, well, does this really work, right? So And so what is the problem here? The problem here is that notice that this chain is not really Markovian. Why is that? Why is that the case? This is because you are using successive approximations, and the successive approximation, the approximation at each step will depend on the previous steps, because in the previous steps we are approximating functions and we are doing random walk proposals. So where the chain really, the trajectory of the chain really depends on not just the immediate value, but all of the previous values. So the first result, there are two results that I will just talk about. I wouldn't go into the technical details, but I would just tell you what the result is. The first result is that the parameter set is compact. Then most MCMC algorithms, I just talked about random walk metropolis, but the Longevin, hybrid Monte Carlo, etc. You have ergodicity. That is that in total variation, the distance between the law of the Markov chain and the target density goes to 0. So this basically means that, okay, at least the ergodic averages of the Monte Carlo for reasonable functions, you expect what they should be. So how do I prove, what is the proof idea? So let me just get all of the, yeah. So here is the proof idea. So because theta is compact, it's a really simple idea. So because theta is compact, an infinite number of models will eventually happen, right? In some set, right? That's this probabilistic pigeonhole principle, and you're evaluating the function infinitely many times, almost surely. So there is some set in which you're going to have infinitely many evaluations. Because you're evaluating the true function infinitely many times, you get to approximate the function to a precision that we like as well. And consequently, this time inhomogeneous Markov kernel converges to the true kernel, right? So the true kernel is as if you'd run the true algorithm with the true evaluation of the function. So this is key to our proof, basically to understand that even if you're approximating, because you are eventually approximating to an arbitrary precision, the Markov kernels converge to the truth as well, eventually. And therefore, we get ergodicity on that small set. And then by an induction, we can really show that you have ergodicity for the entire parameter space as well. So the proof is, that's the proof. It's not that not that hard. But I do want to talk about an important area in Markov chain theory. These are called adaptive Markov chains. Again, the name is like a misnomer, where these are these are not quite Markov chains. These are non-Markovian chains inspired by Markov chain algorithms. And again, started by Gareth Roberts and Jeffrey Rosenthal, we do know how to analyze the ergodicity of such systems. They've worked out some really nice theory and conditions that we can use to prove ergodicity of these methods. I have a slide coming on in a minute. I'll just show you give you two conditions to check the ergodicity of such systems. When this is a second result, and this is useful for algorithmic design. This is also another example where theory actually tells us how to design algorithms. So that's extremely useful. Anytime theory does that, that's super good to know. So here is a result which shows that if in case your parameter space is not compact, in most examples they're not compact, let's say RD, then we can show that if your posterior distribution has Gaussian tails, then you still have ergodicity as well. Now, the ergodicity, you don't need Gaussian tails. You can, the ergodicity also holds under other assumptions, under natural assumptions. But here the proof is more involved, and it turns out that theory tells us that you cannot really do the approximation arbitrary, right? So there's some, this is where most of the meat of the algorithm is, that you have to really respect the underlying dynamics of the Markov chain while you construct the approximations. Why is that? Well, we know that for any Markov chain, in order to have ergodicity, there needs to be a natural mechanism that must be built in, so that if the algorithm is exploring the state space at the infinity, there is a natural way it contracts and comes back to the center of the state space, right? And typically, even to prove ergodicity in these settings, we use Lyapunov functions. And the point of Lyapunov functions is specifically to identify the mechanism that makes it comes back to the center. It turns out that if you do not do the approximation carefully, in particular, if you do not respect the Lyapunov function of the underlying Markov chain, the approximation can mess up so that you don't have ergodicity. In particular, you don't even have recurrence. Right, so the theory tells us that. So it's important to know that when you design these algorithms, that it's easy to mess it up and it's easy to lose ergodicity. Okay. Yeah, and we have simple examples again as informed by theory, which tells us that you do not have ergodic chains. Yeah, this is a slide I wanted to talk about adaptive MCMC. So people who are interested in this, the classic example, it started with Hariu et al., where remember that if you're running a simple MCMC, let's say a random walk metropolis algorithm, you want to know, and let's say suppose you want to propose from a Gaussian distribution with mean mu t and variance sigma. One way to compute the proposal mean and sigma is to take the empirical mean of the Markov chain to be your mean and the empirical covariance matrix of the Markov chain so far to be a covariance distribution. So you can really see that the proposal distribution depends on the past values. So it's not Markovian. Yet this chain is one of the most practically useful devices that exists. It works like a charm. And again, Gareth Roberts and Jeffrey Rosenthal in 2007 worked out a set of conditions, basically two conditions. One is called containment and another one is diminishing adaptation, and shows that if you could verify these two conditions, then you can show ergodicity. Roughly what these conditions mean is that containment means that the algorithm doesn't wander off to infinity. And diminishing adaptation is that we eventually stop adapting in our context, for example, that we eventually stop approximating the function, or the approximation doesn't add too much after a point, right? That's what diminishing adaptation means. Okay, so in the remaining time I have, let me show you some numerics just to see, okay, well, I have to show you that this actually works, right? So here is, there are many variants. So again, you can mix and match, right? You can really use whatever method as long as it conforms to the theory. You can really use lower order polynomials to approximate. You can use Gaussian processes. And also there is no specific restriction on what MCMC kernels you can use. You can use random walk metropolis, you can use hybrid Monte Carlo, Langevin, etc. So let me show you an example. So this is an example where the underlying PDE is from an elliptic PDE from an inverse problem. And I wouldn't go into the details of the problem, but here is what we need to focus on. So this first plot shows you 4 different algorithms. One is the evaluating the vanilla algorithm, which evaluates the function a true number of points. The second one is a linear approximation. Blue is the quadratic approximation, and fourth one is a Gaussian process approximation. So notice that the error, so the Monte Carlo error of the algorithm goes down, not surprisingly, for all 4 methods as the number of MCMC step increases. For example, if you take 10,000 steps in this problem, the Monte Carlo error is within about 2 decimal places. That's not surprising. So the only thing that I want you to take home from this slide is to see that all 4 methods work in terms of showing the right ergodicity. However, if you really look at the true number of evaluations, you can see that the first 2 methods, right, at least the vanilla method, which actually evaluates the function every single time, the number of evaluations increases linearly with the number of steps, not surprisingly. Whereas, and this is the point of our talk, if you look at quadratic approximations or GP, Gaussian processes, the true number of function evaluations is an order of magnitude smaller than the vanilla algorithm. Here is and so if you compare the relative error, the relative error is, for example, the quadratic approximation produces errors within 2 decimal places just as the same as that of the original algorithm, but only using a fraction of evaluation of the true functions. For example, the vanilla algorithm uses 10,000 evaluations here, whereas our algorithm uses about 500, excuse me. Our algorithm uses only about 500 evaluations of the true function, and yet produces the same Monte Carlo error. Here is another example from real experimental data using an E. coli problem. The underlying physical model is a differential equation. Notice that the posterior distribution is as far from Gaussian, right? So we're not, and often even concentrate on a lower dimensional manifold. And again, the same story happens, is that our algorithm performs, our algorithm uses maybe about 1,000 evaluations and produce a Monte Carlo error within 1 decimal place compared to the true model evaluations, where it takes really literally an order of magnitude more evaluations to produce the same Monte Carlo error. Maybe I'll just finish with the problem that I started with. So in the ice sheet example, using the global climate model, we ran. This is what the posterior distribution of the parameters look like. Again, far from Gaussian. And the vanilla algorithm. So, for example, even in this model, like say, suppose the forward model took about 25 seconds to evaluate. I think this is what it does. A simplified version of it takes. For getting 200,000 steps, the standard MCMC, which uses the original functional evaluation, literally takes about 2 months to run, whereas our method runs in about a day, roughly about 50 times improvement, and it uses about 35,000 runs of the forward model, right? Compared to, let's say, 200,000 steps for each chain. So I'll just stop here, but I'll explain one more thing, is that this algorithm is not perfect. The design is delicate. Like, for example, you can ask this questions, right? Does approximation affect mixing? Does approximation affect tail behavior and the recurrence or transience properties of this Markov chains, right? And also, is the approximation so non-uniform that the implied constants in our heuristic blow up? In short, the answer is yes to all 3, right? The design is not trivial at all. We have some results, and the theory guides us to have more sophisticated approximations. But the story is not complete yet, and much more work needs to be done. So I'll just stop with saying, what we've done is introduced a new framework for doing local approximations within MCMC, which is that if you have a function that is complicated to evaluate, and you can still run an MCMC algorithm by approximating the function. And there is definitely room for creativity in choosing, in coming up with interesting approximation ideas, and then our existing and new Markov chain theory tell us if that will work or not. And most importantly, this is really crucial for applications, right? In the US, there are many national labs use many different versions of this problem. For example, weather prediction, you name it, right? Earthquake modeling, etc. There are, for many of the physical phenomenon that we care about, there's always underlying a very sophisticated physical model. And many a time supercomputers are dedicated to getting an answer for a true evaluation of the function. So these kind of methods are super useful in this context because you don't have to have too much computation time to evaluate the function, and yet get statistical inference and get parameter uncertainty. And that's why I think this method has promise for data assimilation problems. And thanks very much. And this paper was published in Journal of American Statistical Association a couple of years ago. And we are working on few variants on the algorithm. And if people are interested, please send me an email and I can give you more references. And I'll stop there.
Okay, thank you very much. Let's thank Natesh. Are there any questions or comments? If not, I can start with one, which is, I mean, of course, it's a trade-off. So you said in the last slide, just the previous one, you said something about, so maybe the previous one, actually.
Yeah, this one.
Yeah. So even before, and I'll come to this as well. I have a question on that. But really, you're making an approximation. And so you had showed all the run times are going down and, things like that. So, of course, you're gaining something and you're losing something, right? So because you're making an approximation, and do you actually have bounds on the degree of your approximation? What are you losing? And so you're losing in accuracy, perhaps.
Yeah.
And so do you know what that trade-off is? And
yeah, so I do know. So the results I just showed you so far was purely qualitative, right? Which is that you have ergodicity eventually. Yeah, what you're asking is sort of the bias variance trade-off, which is that if you run the algorithm for, I don't know, 100,000 steps, how big are your confidence regions, right? Yeah, so I do know that only for specific examples. The reason is that I need to know what a Lyapunov function, so we do know that if a Markov chain is geometrically ergodic, there is an underlying Lyapunov function that makes it do that. But in practice, that's an existence result. We don't really know what is the Lyapunov function. At least I don't know how to construct it in the examples that I care about that easily. But in specific situations where I actually know what the Lyapunov function is, I can explicitly work out the trade-off of the approximation error versus the sampling error. I can do that. And that is definitely the advantage of the method there is that we can really separate where is the error that is coming from approximation versus where's the error that's coming from sampling.
Okay, there's a related question by Shrikar. So he asked, getting rates of convergence of adaptive MCMC is already a challenge, particularly in non-compact domains. So could you elaborate about the mixing issue due to approximation plus adaptive MCMC?
Yeah, so I think the key mixing issue is the following, right? So imagine that imagine that you show ergodicity using a Lyapunov function, let's say that's quadratic. And you're using a cube, so you have a quadratic function that is your Lyapunov function that's the mechanism that makes your chain turn to the center from far out in the state space. Now imagine that at the tails, your approximation is cubic, so that the approximation can really produce an error of magnitude higher order than what is required by the Lyapunov function for the function to turn back. In that case, forget mixing. The chain can go from positively recurrent to null recurrent to not recurrent at all, to being transient, right? So the approximation truly can change to make the chain from recurrent to transient. So this is why in the non-compact case, our results are, there's much more work to be done about even establishing mixing results of how do you choose your approximation so that you don't even lose recurrence. I don't have a general theory for that. I only have heuristics, and all of the heuristics comes down to this following thing, which is that find a Lyapunov function and make sure that the contraction as specified by the Lyapunov function still happens even after the approximation. And that makes sense, right? Because you're messing with the transition probabilities by messing with the proposals. Therefore, that's the thing that you need to control. But beyond that, unfortunately, I don't have an overarching principle that tells you how to control that.
Okay, thanks. Shrikar, if you have any follow-up questions to that, feel free to. Okay, great. And are there any other questions or comments? And there's also the issue that, of course, you said, you can talk about all of this just in the one-dimensional case to begin with, even d equals 1. But as Gareth had mentioned, so are there also high-dimensional issues here that one should sort of be aware of?
Yeah, for sure. I think the approximation is not free, right? Like even in high dimension, you're approximating a function. You really need to d squared points to come up with if you're doing a quadratic approximation, you roughly require O to d squared points to have not have an underdetermined system, and d squared is quite a lot, right? If you're in 100, it's about 10,000 points. That's quite a lot. So all of that. See, my motivation, maybe I should have mentioned this in the beginning. My motivation for this problem was to make this work. Like even in the cases where we know how to do the MCMC, this is this additional problem that there's a no-go because we couldn't evaluate the function. So we just wanted to come up with methods that solve that particular problem. But of course, we haven't solved all of the other problems that's inherent in this. So all of that makes our life incredibly, doubly difficult. Let me put it this way.
Okay, thank you. If there are any other further comments, if there are not, then let's thank Natesh again for a very nice talk and
Thanks very much.
opening up another sort of set of problems to think about. Yeah, and I think we have 3 minutes before we start the next talk.